Ladies and gentlemen, we ask that you please take your seats at this time as the program will begin momentarily.
While in experimental research, we manipulate variables, also known as the independent variable, and this manipulation can either be done between groups, known as the independent design, or within the same group, known as the repeated measure design. When there are more than two groups, we can use the ANOVA test. Both t-test and the ANOVA test are used to compare means between groups. This is a demonstration on the use of Jamovi to conduct an analysis of variance, also known as ANOVA. We use ANOVA to compare means when there are more than two groups. We'll open a dataset that comes with Jamovi in the data library. Click on the menu bar, Open, Data Library, and select Anderson's IRIS data. We'll start with inspecting the dataset. There are 5 columns, and 4 columns are measured on a continuous level, and they are the dependent variable, sepal length, sepal width, petal length, and petal width. Species is measured on a nominal level, and there are 3 species of iris in this dataset: Setosa, versicolor, and virginica, and species is the independent variable. For the purpose of this demonstration, our research question is whether the 3 species of iris have different sepal length. The null hypothesis is that there is no difference in sepal length across the 3 species. Let us first take a look at the descriptives. Click on Exploration under Analysis and select Descriptives. Transfer sepal length to the variables on the right-hand side, species as split by. For the statistics, we can look for normality using Shapiro's wheel and create histograms with density plots. The sample size is equal across the 3 species. Looking at the means of the sepal length, Setosa is shorter than versicolor, versicolor and Setosa are both shorter than virginica, but we do not know whether these differences are significant. The histogram shows that the data across the 3 species are normally distributed, and the p-value for the Shapiro's wheels is more than 0.05, indicating that the assumption of normality has been met. With this information in mind, we can move on to the ANOVA test. Click on ANOVA under the ANOVA tab. Transfer sepal length to a dependent variable, and the fixed factor represents the independent variable species. For the effect size, you can select either the eta square, partial eta square, or omega square. And for the assumption check, you can look for homogeneity tests. We'll leave out normality tests since we have already looked at it in the descriptives. Looking at the Levene's test for homogeneity of variances, the p-value is less than 0.05, suggesting that this assumption has not been met. And the results of the ANOVA is less than 0.05, and this suggests that sepal length differs significantly across the 3 species, but we still do not know where the differences lie. So we need to conduct some post hoc tests. Transfer species to the right-hand side. We'll use Bonferroni correction for the p-value and Cohen's d with 95% confidence interval for the effect size. The results of the post hoc test shows significant differences across the 3 species, and Setosa being shorter than versicolor. Setosa is also shorter than virginica, and versicolor is also shorter than virginica. We can visualize these results by creating plots with the estimated marginal means. And this plot clearly shows that Setosa is the shortest, followed by versicolor and virginica. And this difference is significant. Given that the assumption of homogeneity of variances has not been met, we can also conduct the non-parametric version of ANOVA, known as the Kruskal-Wallis. Select the Kruskal-Wallis under ANOVA, transfer simple length and species to the correct boxes. Looking at the results of the non-parametric Kruskal-Wallis, p-value is less than 0.01, suggesting that the differences across the three species is significant. This is the end of the demonstration for ANOVA.